Hello, everyone. Welcome to ByteStruct. Um, so we're gonna try another problem. So imagine you're in a system design interview. The interview says design a rate limiter. Um, Most candidates they immediately grab the marker and start drawing the boxes, right? So load balancer here, server here, database there. They look busy, they look confident, um, and they fail because they skip the most important part of the interview. Today, we are going to do this question the right way, maybe 5 steps. First is the requirement first, right? So understand the requirements, then go with the capacity, um, and then high level design. And third will be kind of a deep dive on the algorithm being used for this. Um, and then we'll wrap it up, right? So by end of this video, you will know this question like cold, right? So let's go. So step one, right? So just to show you, you have a request of 50, right? So rate limiter is nothing but it's like imagine a bouncer standing outside of a club, and your club only allows 200 people, and if the people are more than 200, then bouncer is like a rate limiter. It doesn't allow. So in this example, bouncer is a rate limiter. Um, that's in the software. And then imagine you want to put a rate limiting on your APIs, right? So that's how it's called, rate limiter. So imagine you have a request, and which we handle mostly, let's say 100 requests. And if the request is 50, it's under limit, you're good to go. You can go to the back end and return back the data, right? So, but if you hit the 101, which is over your limit, I think we have to return back HTTP 429, which tells you that, hey, after this time, you can retry this service. So that's what the rate limiter will do. So going on the step one, which is basically um, the requirements phase, right? So before you touch, right? I think the questions we should ask interviewer. These are some of them. You can add more, but first is like whether client side or server side. So server side, right? Always, right? So client side rate limiters are worthless. Um, they they doesn't mean anything, right? The client controls their own code. They can just remove the limit. You need to enforce on your side. Um, then basically, what do we throttle on, right? Is it an IP? Is it a user ID, API key? What should we look at to say this has hit the rate limit, right? So this is where most a login endpoint should be limited to, let's say, 5 per minute per user. A search API might allow 1,000 per hour per hour request, right? So the answer is flexible rules, right? Different endpoints get different limits. So we might have to configure maybe different endpoints with different limits. What scale are we talking about, right? So it's a big application. So 100 million users distributed across many servers. Um, and then do users know when they are throttled? Like, do we have to send them back any error message? As I mentioned, like it could be HTTP 429, which says, okay, retry after this much minutes, right? You can have a conversation around these topics as well, which basically, like, do we need to be too accurate, or we are flexible? Does it 100 means that 100, or we flexible? It can your server can handle 103 requests, which I think you should be flexible enough. And then what's the low latency, right? So all of this rate limited logic should not take a lot of time. It should be less than 5 milliseconds, right? The user should never feel it that this is what we're doing. Memory efficient, right? All counters live in RAM. For distributed, uh, it's for the distributed shared counter state across all the servers. And exception handling I mentioned here. Fault tolerant. If this system goes down, what do we do? Um, so these are different dialogues you can have with your interviewer. So now, if we talk about the capacity classification, right? So we're talking about scale of like 100 million users, right? Every counter, right, is user ID or window key mapped to an integer counter. The user ID tells you who who is the person, right? The window key scopes the counter to the counter time window, so it resets equally. So after automatically, right? So in Redis, right, it looks like something like this. You have a user ID and then you have a timestamp, right? That timestamp is rounded to the current minute. The expire, basically the expire auto deletes the counter after 60 seconds, so you can never commute stale data. So 1 million active users, 50 bytes, for example, it takes. So we're talking about 50 MB. And basically Redis laughs on 50 MB because memory is not a bottleneck here. So don't spend another second on it if you're going with Redis. It should be fine. Then talking about the throughput, right? So we have almost like 100,000 requests per second, 100,000 Redis operations per second. Um, a single Redis node handles like 100K to 300K operations per second. For more shard, you can do the sharding on the Redis cluster by user ID, which can also help. Also, then about latency, like half a millisecond, right? And then you're doing some computation of increasing Redis integer or calculation, incrementing, expiring. That takes, let's say, 1 millisecond, which comes up to 1.5 milliseconds. And we said like this latency should be less than 5 milliseconds, which is, we still have enough room to breathe, right? So still 3.5 millisecond of a room. So let's talk about high level design, right? So before like drawing anything, right? Where does the rate limiter lives, right? That's the biggest question. So we have multiple approaches. I think there are three approaches in short. So first one is inside each app server, right? Which is looks faster. So fast, simple, right? So but you have 20 servers, right? So each one keeps its own local counter from Redis, right? A user sends 100 requests spread across, let's say, 20 servers. Each server sees like around, if I do quick maths here, so if it's 100 by 20, right? Which is basically each server kind of gets the 5 requests, right? If load balancer is equally distributing the requests, which is well under the limit, right? But globally, if you see the user just sent 100 requests and none were blocked, right? You failed silently. This option does not work at scaling. So this is big no, right? Then option two is like having a API gateway. So you can use Kong AWS API gateways, which basically does all of this for you, right? So all traffic passes through before it reaches any service. So rate limiting is basically built-in plugin kind of thing. You can configure it, you don't write it. This is industry standard. If an interviewer asks where the limiter should live, start here, right? Option two, right? So, but I don't think so. This is an option, but I think in this question, I think basically interviewer is more interested in how do you design your own option, like on limiter, right? So this is what you build when the gateway built-in limiter is not flexible. So option two is like Amazon gateway is not enough flexible. So how do you build it, right? So this is the option three basically. Custom logic, your own service sitting between the gateway. So you have a gateway, and then this is the architect for here. So you have a gateway, and then here you have your rate limiter, right? So this is what you implement. So client hits the API gateway, and then gateway passes the request to the rate limiter service, and then rate limiter checks in the Redis, right? And then if the counter is under the limit, the request goes to the backend service. that means it's allowed. If it's over, then we return back the 423 response. Now, the rules don't hard code limits, right? So the best thing to do is like have a YAML file, don't hard code. You can have like a domain, for example, auth, related to auth. You have login service, which basically handle only 5 requests per minute, So you can configure this in the YAML and give it to the product kind of product owners or people who can configure these things, right? So auth, like let's say auth has a login that's 5 per minute, or maybe another example is messaging, right? So messaging has a marketing as a value, and then marketing can have 5 per day request, which we rate limit, right? So this is like a YAML configuration which you can do, and product can change a limit without a deployment, so you don't have to redeploy your code, and always include these headers in your 429, right? So what's the rate limit, how much you have remaining, and how much retry after, how much time you can retry after. So the last header, basically, I think most of the people forget this. It's what lets the client back off immediately instead of harming your system. So I think it's good to send it back saying at what pace they can try again. This is deep dive now, right? So how do we actually implement stuff here? Like what do we do here? Like what's the strategy, right? So in general, I think there's like 5 algorithms, right? So there's a good article around this. We can quickly go over them. So token bucket is one of them. Imagine a bucket, right? It fills the tokens at a fixed rate, say 10 tokens per second, and every request consumes one token, right? If the token is empty, the request is rejected, right? AWS is the one which uses this. Stripe uses this. It's O of one memory because it's straightforward, just 2 numbers per user. The current token count and the last refill timestamp, and it handles bursts naturally. If a user hasn't made request in a while, tokens accommodate and they can spend them all at once. So if I have to show you how this is, I think this is a good article. So token bucket is, you have a bucket fills with the token at a constant rate, and then your new request takes the token and goes through this, right? So if you're running out of the tokens, you drop the request basically. The issue with this approach is basically, also there is a good article on byte go. So if you see here, right? So basically you have a refiller, and then if you are, this is the approach, you have a refiller, and then if you're overflowing. But the problem with this one is, like here you have a refiller, your request comes, if there are not enough token, you drop the request, otherwise you go through it. The problem with this approach is there are 2 parameters in the algorithm, which are bucket size and token refill rate. Those are very hard to fine tune, right? So like basically that's the challenge here. What's the bucket size, right? And what's the refill rate here? If you get them wrong, and you either over restrict or under restrict, right? So you need to be careful. So that's why this approach is hard to fine tune basically. Now looking at the second approach, which is leaking bucket, this is pretty different than the first one. And this one is I think this is good illustration. Like if you have a bucket which is filled with a constant rate, and then you have a small hole down there where you have a leakage right there. So this is like a FIFO, right? So your leaky bucket, and then you have, imagine a queue after this, and then you're taking out the stuff from queue. I think the best illustration is this also. So you have a request, you have a bucket, and then you have a queue, which you are processing at a fixed rate, right? And and your output is smooth, right? Granted stable throughout to your backend. If the queue fills up, new requests are rejected, right? Um, this is great for protecting slow downstream services, but burst fill the queue fast, which means new requests will start waiting, right? They will wait in your bucket. I think the challenge with this one is also a burst of traffic fills the queue with the old request. So in this case, the queue is technically is what the bucket size is. Like this is the kind of you don't know. Um, I think that's basically the burst coming in there can fill up your bucket, and they're not processed on the time, right? So that's hard. There are two parameters in the algorithm. It might not be easy to tune them. Again, the challenge here is this bucket size and then this hole right here, like at what rate you take it out and what rate you put it in. So that's kind of a challenge there. Then there is another one. I go back. So just to go over, so this is FIFO, and then this is stable, predictable output, protects slow down streams because you're taking slowly out. I think the issue is burst fills the queue and your request drop. When I say queue, like your bucket is piled up, and now your new request, because in the bucket you keep storing your requests, and then you're taking it out at a slower pace. Hard to fine tune those params, right? Now the next one is interesting. It's called fixed window counter. So in this one, what happens is so it's simply one counter per minute, right? So let's say you have maybe let me see. Yeah, so let's say every minute, like every so let's say you have I know the timer is 1 second, so maximum 3 requests. So you can handle maximum 3 requests, okay? So per second, right? So each second, right? You're getting here you got 3 requests, which is fine, but here you got more than 3 requests, right? So you have a cut here, right? So if more than 3 requests are received, extra requests are dropped, right? So in this case, these are dropped, and then that's it, right? So in this case, you have kind of your fixed window, right? So you said for per second, I can only do 3 requests. So you look at that second, right? And then you move to the next second, and then you move to the next second, right? So it's like that. I think the issue is with this one is with the edges, right? So when I say with the edges, is basically imagine here, right? So you have two here, and 201, and then 202, right? So let's say you have, if you pay attention here, this is fine. You have one fixed length, right? So one fixed. This is sorry. This is one, right? So I think that the main issue is the edges here. So if you look at this, this is also also once per minute. If you read this, the system allows maximum of 5 requests per minute, right? That's the assumption. And the available quota resets after a minute. As seen, there are 5 requests between 2 and 2:1, right? So between this, there are 5 requests, which is good. So you permit it. So this is all fine. But if you pay attention between this and this, there are and 5 more requests between this, right? So between this and this, there are 5, and then you have 5 more here, right? For 1 minute window between 2:13 to 1:30. So you see, like here you have 5 requests, and here you have 5 requests, which works fine. But if you pick this window in between, you have more than 5, right? Which is 10 requests. this is twice as many as allowed requests. So it's little buggy, right? So you, with the edges, you don't know what's going on, right? Um, just to give an example, right? So let's say limit is like 100 requests per minute, and user sends 100 requests at 0.59, right? Where your window resets, right? They send another 100 requests at the next starting minute, right? So in a window, you have kind of you have done like 200 requests, double the requests, right? This is also called boundary spike problem. Any user who knows when your window resets can exploit this, right? They can double their effective rate limit at every boundary. Um, so that's why in production, fixed window fails this test. Use it only for simple internal tooling. It's not scalable. So that's why we have here a bug of 100 requests at 0.59. Then again 100 requests as this, which is 200 in 2 seconds, which is 2x of your limit. So this is again a no. Then going back to slide, there is new one which is called sliding window log. It's very similar to sliding window algorithms. So what do we do here is basically, I go here. I think so. So maybe this example, right? So what happens is we have let's say we allow 2 requests per minute, right? So we have a logger on the side, right, where we log whenever the request comes, right? So you have kind of a log, and then you have also your your windows, right? So basically, let's say a request comes, and then at 10:30 there is another request comes. So we look at the log looks fine, you have 2 requests, we can do 2 requests per minute, so far so good. But then 10:50 there's a third request, so now your log size is increased to 3, which is beyond 2 requests. So we will not serve this request, okay? And then 101:40, what happens is, because now you have surpassed your 1 minute, right? So your 1 minute is finished. Now you surpassed your 1 minute, and now you can slide your window, right? So you can take out these 2 entries, right? And then your window is now bigger by taking this out. So here the log is empty when the request arrives. Then the request is allowed. The new request arrives at 103. The timestamp is this, inserted into a log. And after the insertion, the log size is 2, which is good, not larger than the allowed count. A new request arrives at 150, and the timestamp is inserted in the log. And after the insertion, the log size is now 3, larger than the allowed size. So therefore, the request is rejected, even though the timestamp remains in the log. So that's why we rejected this dude, right? So a new request arrives at 140. Request is in the range, right? So it's still in the range, right? Basically like 140 to 140 is like a minute, right? So which is also good. So this is in the range and within the last year, but requests sent before 140 are outdated. So that's why you took it out. So it's like a sliding window, right? So 2 outdated, we took it out. And after the remove, the log becomes 2. Therefore, the request is accepted. So we accept this one. So this is good. Rate limiting is very accurate because you have now sliding window, no more that bug. The issue is like you're now introducing a separate kind of a log segment, which is consuming a lot of memory over the time. So that's the drawback of this. So going back, this is off and per user memory, too expensive to scale. So then I think they came up with the approach, which is mix of sliding window and the fixed window counter. So you see window counter is there and the sliding is there, right? So it's a mixed approach. How is it different? Let's see. So in nutshell, what happens is, like, let's say you have a fixed window, right? And imagine this is 100%, right? So if I say this is 30% of 100%, right? So you slide back, even though you have a fixed window, you slide back to 70%, and you look at your requests. So in this 30%, you got 3 requests, and then you go back and look at the other requests. So you have like 5 requests here, which sums up to 8 requests, which you're doing at current time, So it's interesting. You can read more about this. And it smooths. I think this is the best approach you should explain to interviewers, saying, um, you know, this is the one which is mixed of both and better approach. And now, I think as you know this one, now I think we're gonna wrap this up. So there's a token bucket, leaking bucket, and then fixed window. We'll talk about sliding log and sliding fixed window, right? So this is the approach you should go with. But in nutshell, you start with the requirements, you estimate your capacity, what we did so far. We did API gateway for the placement, where do we want to put it? Then we went with sliding window counter, and then to return back, we decided port 29 with the rate limit headers, and then we used Redis, which is one counter per user, as a cache mechanism and one source of truth for us. And that's it. With this, I'm gonna wrap this up, and then see you in the next designing problem. Stay tuned with Byte Structs. Thank you so much.